So today I want to tell you a bit about how we've been using multi-objective optimization to study intermittent swimming in fish. So when I say intermittent locomotion, what exactly do I mean? You've probably observed this in animals. They never move continuously for a very long time. They often will move for a bit, then rest for a few seconds, then keep moving again. And depending on the species of the animal, this sort of pauses can last from a few milliseconds to minutes. And people have noticed that about half of the total locomotion time is spent in this sort of intermittent manner. Here's a video of a swordfish that's chasing after a small group of fish. And you'll notice that it moves in a quick burst and then glides for a few seconds. So in this case, it's mainly for directional control, but this happens even in birds. Here's a bird flapping its wings, and then it'll fold it in, fly on a ballistic trajectory for a few seconds, and then flap again. So the focus for my talk today will be on zebrafish. Here's a high-speed video slowed down to about 10 times slower, and you'll notice that the zebrafish never move in a continuous manner. They always beat their tails a few times. And you've seen this in aquariums. The fish never move continuously. They beat their tail a few times and then glide silently for a few seconds. And this mode of swimming is called burst coast swimming. And people have postulated that this sort of motion has many advantages. It can save It can save energy for the swimmer, and it also reduces the disturbances the swimmer generates in the water. And it has the advantage of not alerting both prey and predators. Another advantage is, imagine that you're running and you're moving your head sideways all the time. You would tend to get disoriented. So a short pause helps them to stabilize their sensory field. One disadvantage is that it reduces the average speed. But again, it's a type of behavior that is not used in life-threatening situations. Okay, so with all of these advantages, any sort of behavior that gives you an advantage is very important because it can help you compete with rivals. So it gives you an evolutionary advantage. Unfortunately, most studies, both theoretical and computational, of swimming has considered steady motion, as shown here. There have been a few studies looking at intermittent swimming, both theoretical and numerical. One numerical case is mentioned here, but they have some limitations. In this case, the burst coast motion was specified a priori. Our goal today will be to see if we can discover the best way of swimming intermittently with two goals in mind. We are after high speed, and we are also after minimizing our energy expenditure. All right, so we will go about doing this with the help of multi-objective optimization. And it's very useful, especially when considering two conflicting metrics, which is the case here for us. If we swim with high speed, it's very likely we won't be very efficient. And the advantage of multi-objective optimization is we don't get a single answer. We get a set of answers. And if you were to consider a robotic swimmer, so that's a robotic swimmer swimming continuously. And the handler of the robot can pick from the list of behaviors depending on the task he wants to achieve, right? So if the handler says, I want high endurance, you pick a certain set of parameters, or if you want high speed, you pick another set. One more advantage of using numerical optimization is we are not limited by biological constraints, meaning if you are considering body shape, you're not limited by how organs are arranged inside the body. Okay, so let me just quickly walk you through the numerical methods we use We're basically relying on the Navier-Stokes equations, both 2D and 3D. Here's the 2D vorticity equation. And the way the solid talks with the fluid is done via penalization. So there's an extra penalty term added here, shown in green. The software we use is very nice in that it allows the grid to be adaptive both in space and in time. So we save a lot of computation compared to if we were to use uniform grids. And it is open source, so you can check it out over there. Also, I'll show you some 3D results, and for that, we've used a finite volume solver. Okay, so we will be talking about energy efficiency. So let's describe a few relevant variables. So efficiency we can define as useful power, that's in the numerator, over the total power. But the quantity we'll focus on is called the cost of transport, which is total energy spent over the total distance traveled. So it represents how much energy you need to spend to travel a unit distance. If you think in terms of car, it's just how many liters of petrol per kilometer. Okay, and these quantities keep varying periodically. So here we're looking at efficiency as a function of these two quantities, P thrust and P def. And as the fish keeps beating its tail, the efficiency keeps going down and up. And we know how to do these steady swimming cases quite well. How do we jump to an intermittent form? So we used the simplest way we could think of. So we just introduced a modulating amplitude. Ignore the equations, I'll show you visually what this means. So if you remember, there's the steadily swimming swimmer, and we say that the amplitude, the maximum amplitude can drop from 1 all the way down to 0. So the behavior changes to this intermittent form. And this sort of modulation gives us 4 parameters that we can play with. There's time taken to decelerate from 1 to 0. And delta t cost is how much time you spend at 0 amplitude. So, and then you accelerate back from 0 to 1, and then you have the option to spend some time swimming steadily. So there's our 4 parameters that we can optimize with. And again, if you remember, we are after 2 objectives. That's high average speed and low cost of transport. Okay, so since we have 4 parameters, doing a systematic search is not a very good idea. If you just consider 10 different cases for each of these 4, that's 10 to the 4 cases you need to run. So that's another reason why optimization is a good way to go about doing this. Okay, all right. So how does the optimization exactly work? We use a genetic algorithm called NSGA-II. It's a non-dominated sorting genetic algorithm. And it's a very commonly used, very popular algorithm which works very well in many different cases. So the way it works is for the first generation, we have no idea what a good population would look like. So we initialize randomly. And once we have these, let's say 32 individuals, we run 32 simulations to evaluate their fitness, basically to figure out what the average speed and cost of transport is. And then when we have the result, we can select the fittest from that population and allow them to mutate, allow their characteristics to mutate and crossover, and to create children for the next generation. Okay, and and we keep looping this procedure until we get the desired population. So another important thing for multi-objective optimization is the Pareto front. Let me explain what that means. Okay, so if all of this represents the initial population, the orange individuals represent the best among that population because these are the objectives. So this might be speed. So high speed is preferred and low cost of transport is preferred. Actually, this is usually negative speed and cost of transport. So you want to minimize both quantities. And the good thing about all these individuals on the front is no other individual is better than any of them in both respects. So all of these are optimal in their own right. Okay. The code we used for NSGA-II is actually open source, again, by Dave et al. And it's a serial code, so we had to figure out a good way to parallelize it. And for that, we used another library that was also developed in the group. It's called Torque, or Pi4U. And there's reference 1, and there's another reference. So the way this works is, it's very similar to how OpenMP works. You basically take serial code, and you can parallelize it. Usually, I don't show code, but I think right now it would be, it's going to be very useful. So this is your function evaluation. In this case, it's just adding 2 numbers. But for us, this would represent a simulation. So this would be a full fluid simulation. Okay? And you have the driver. So this is the NSGA code that drives 100 different simulations. Okay? If you were to parallelize this with OpenMP, that's just a single line, right? But we are limited to a single node in this case. But remember, I'm running 100 different distinct full Navier-Stokes simulations. So to run them distributed, with Torque, all we need to do is add these 3 lines. That's initialization, that's calling the function, and then waiting for everyone to return. That's it. So it's a it's almost zero effort compared to if we were to go and change all the serial code to MPI. We have to, all of the communication is hidden from us. So that's a very big advantage. Okay, the way this works is there's a number of worker threads generated, and each compute node gets 1. Every time the worker completes its task, a server thread asks all the other workers if there's some leftover work that they can steal from them. Okay? And this basically means that the number of simulations we launch has to be larger than the number of workers. And another way of saving time is we schedule the simulations that we expect to take the longest to run first. Okay? The way this works is via an artificial neural network. So during the first few generations, we don't know which simulations will take the longest, so we record how long they took and what are the parameters they were running with. And when the network is trained, then it can predict with some accuracy that this new set of parameters, the simulation will take this much time. And then then the simulations are scheduled accordingly. The ones expected to take the longest go in first. Okay. In terms of efficiency, this is the strong scaling for MRAG. MRAG is the fluids simulator that we use, and it runs on a single node. That's the number of threads, and using up to 8 threads, we retain about 75% efficiency. And this shows the efficiency for a single optimization campaign. So remember, we were working with 32 distinct simulations running simultaneously, each generation. So if I were to say each simulation goes to a distinct node, that would be this case. Number of nodes is 32. And then the parallel efficiency is terrible. This is exactly because of the load imbalance. And if we schedule this, just schedule this with 2 simulations per worker instead of sending each simulation to each different node, we get almost 90% efficiency. Let me show you something else. Okay, so we've already seen that with naive scheduling, we only get 50% efficiency. But if we do this runtime-based scheduling along with multiple simulations per worker, we get almost perfect parallel efficiency. So it's very, very effective. It doesn't require a lot of work, but the return is very nice. Okay, so now let's look at the results. What do these Pareto optimal swimmers look like? Okay, so again, this is the starting population. In blue, you see the optimal individuals, and in gray will be individuals that get rejected. So after each generation, you get a new set of optimal individuals, and the old ones keep getting left out. Okay? And we will look at two different cases. One for smaller fish, which represent larval-sized fish, and for larger fish at a higher Reynolds number, which represent what adult would do. Okay, and once we converge to a final population, we can pick 3 different individuals, 2 on either extreme. So one over here, one over here. So let's see, that's the fastest one. Okay, now that's the fastest one. We can look at that guy, and we will also look at the most efficient swimmer. And then we'll pick someone in the middle to see what a nice combination looks like, okay? And here's the result. Okay, so this is an animation showing the result from the efficient swimmer on top. The generalist, maybe I didn't define this. Generalist is a swimmer that has a nice, a very appealing combination of both speed and low energy expense. And the fast swimmer. And this is for a larval fish, okay? So let's see how this went. So you'll notice that the efficient swimmer prefers to spend a lot of time coasting. So it prefers to beat its tail a few times and then glide along silently. The generalist spends a little amount, some time coasting, but it's mostly beating its tail quite frequently. And the fast guy doesn't like to coast at all. And there's physical reasons for these. I'll explain in a few slides. All of this is completely the outcome of optimization, and it gives us behavior that we see in nature. So that's one very nice thing about this sort of approach. And if we look at the metrics, so we are after 2 metrics, right? Cost of transport and average speed. We will see indeed that the efficient guy saves about 40% in terms of cost. The fast swimmer is 3 times the cost, but also 1.5 times faster. Okay, so this is for the larval swimmer. What happens when we look at the adult swimmer? Nothing changes in these simulations. The only thing we changed was the viscosity to get to the correct Reynolds number. And again, the efficient swimmer tends to coast along for a long time, and the generalist does a combination of coasting and steady swimming. But this time, the behavior for the fast swimmer is different from what we saw earlier. This time, you do get a lot of coasting. And if you think about it, it makes sense, because when you are a larva, the viscous effects are very, very high. So every time you stop beating your tail, the drag is so immense that you will slow down quite a bit. So there's no way that a coasting strategy would work for a fast larva. Okay? If we break down if you remember, we had 4 parameters to play with: delta T, deceleration, coast. So this is just a breakdown of what each of the swimmers, how these parameters look like. So for a larva and an adult, the distribution is almost identical. You spend a lot of time coasting and almost no time steady. That's the light gold. And you spend some time decelerating and accelerating. The biggest difference actually comes in the fast case. So again, we've already talked about why the reason why, but here you can see it very clearly. The fast larva prefers to swim steadily, but the fast adult prefers to do a lot of coasting. Okay? So what we did from this point was we had converged results from 2D simulations. And we used these as a starting point for 3D simulations. And here's what the results look like. So the body of the 3D swimmers here is colored with thrust. And so whenever you see golden color, it means that section of the body is generating positive thrust. When you see black, that section of the body is generating drag, as in the head over here. So in this case, the fast swimmer actually, one more thing we changed was now we gave the swimmer another parameter that it can decide on. That's, if you remember, the amplitude went from 1 to 0. Now that 0 becomes x. X can be picked by the swimmer. So the fast swimmer actually prefers that x equal 1. So it doesn't like any intermittent swimming. This is different from the 2D case, and I think it's related to the to vortex stretching that doesn't happen in 2D. But we're still looking at why the behavior is different. If we look at the generalist, again, it accelerates quickly, and then it slows down its body undulations. The most efficient swimmer also accelerates quickly, and then almost comes to a standstill, but not quite. So that's a difference from what you see in real fish. They usually come to a complete standstill. And that might be related to fatigue. So you stop moving your muscles completely to overcome fatigue. But if you're thinking about a robotic swimmer, you don't need to stop completely, right? And if the optimizer says that this is the best way of swimming efficiently, then we should implement these sort of controls. So that's most of what I wanted to show you. Let me just quickly remind you what we saw today. So we've used multi-objective optimization to discover intermittent swimming modes that we observe in nature. And we've also looked at how we can very easily parallelize serial code using this tool that I mentioned. So let me stop there and take any questions you might have.
This paper is open for discussion and questions. I have one.
Yes.
Would you please explain the interpretation of the colors on your visualizations?
Sure.
For example, starting with the 2D ones.
Okay. Yes. Let me see. You mean what the colors mean here?
Red, blue, yes.
Okay. So the colors are basically vorticity. So red would be, let's see, I think it's flipped. No. Yeah, so red is fluid swirling this way out of the plane, and blue is fluid swirling into the plane. Okay. And for the 3D cases, the color, again, is the same thing. So it's in 3D. So if you look over here, that red segment is basically fluid swirling this way. And the body is colored with thrust.
Okay.
Hey, thanks for the talk. Really interesting. Have you thought about using multi-population genetic algorithms to improve the convergence of the genetic algorithm?
What do you mean by multi-population?
So here you use one population with like multiple individuals that you try to send to different processors.
Right.
But you can also use multiple populations that are exchanging, like individuals are migrating in between population. And this is usually used to like improve the convergence of the algorithm.
This is done by changing the parameters, like the random seed you use.
So you have different population evolving, and then there's
that's generally used in evolutionary optimization, but we cannot because these are very, very expensive, the simulations.
Okay.
So we're limited in the number of runs we can do.
Okay, but because you are not using the full Piz Daint in your simulation, right? When you are running the genetic algorithm.
No.
Okay.
We're using a few hundreds of nodes.
Okay,
at
so
the same time.
it could extend the scaling of your
Yes,
approach.
we could. Yeah.
Thanks.
So how expensive are they?
So the 2D simulations, when we do optimization, we usually run a lower resolution, and each simulation takes about 2 hours. And in a production run, each population is about 64 individuals, and you run for about 20, 30 generations. So that's 180 into a few thousand compute node hours. And the 3D simulations are much more expensive. They can be a few tens of thousands.
Have you looked into engineering the performance for improvement?
What do you mean by?
Trying to decrease time to solution? Individual.
Yes, the 2D code we have tuned, well, computer scientists in the group have tuned very, very efficiently. The 3D code, though, we need to work on more, because right now it's a uniform grid. We need to go to block structured grid. So.
Okay. Yes, there's one here.
Just one question about the parameter choice for the genetic algorithms, because it's a method that depends on parameter the mutation rate, the size of the population, and so on and so on. How did you validate the choice of your parameters?
The parameters for the...
For the GA, the one for the genetic algorithms. Because as it's very expensive to test it, so do you have some kind of heuristic to select the correct parameters, or just...
You said, how did we validate it?
No, maybe not validate, but did you test it a little bit?
How did we pick it?
Yes, exactly,
okay.
yes.
Yeah, it was... we started off with the smallest population size we could go with, right?
Yes.
So we started off with 16. Then we saw that the Pareto front didn't look very nice. Mm-hmm. So we kept increasing the number of individuals until we got a nice smooth front.
Okay.
But yeah, we cannot conduct like a hyperparameter search.
Yes, of course.
Yeah,
yes.
it's difficult. Yeah.
Mm-hmm. Okay. Thank you.
Okay, so seeing no more questions, let's thank Siddhartha again.